electrochemical kinetic. So, when I spoke about the thermodynamics, I've introduced how basically the electrochemistry can be studied from a physical point of view in terms of thermodynamics and even in terms of kinetic. If the thermodynamics give us with the Nernst equation, the relationship between the free energy of a reaction and the electric potentials and the Pourbaix diagram, every time informations only regarding the stability of a certain species in specific condition. The kinetics gives us information about in which way the speed in which the process are proceeding can modify the conditions described in the thermodynamic. What does it mean? We know that in thermodynamics, for instance, we have described the relationship between the reduction potential and the pH, and in general, basically the meaning of a reduction potentials of one electrode associated with a certain specific redox couple, a certain specific semi-reaction of reduction. So we know that each single semi-reaction has its own specific reduction potential. But the reduction potential that we have described in the Nernst equation, the same that we can appreciate for the resolutions of the Pourbaix diagrams, describe reduction potentials referring to a situation that is an open circuit, in which basically the resistance is going to infinite and no real flowing of current is present. What is happening is that, remembering the situations of the calorimeter, speaking about thermodynamics, this is the example of the zinc oxidation, we know that in the moment in which we are decreasing the resistance, moving away the resistance from the infinite wall previously imagined, we are basically increasing the speed of the process. So if we speed up the process, we are even decreasing the useful work. We are moving away from thermodynamic reversible conditions, and so we have an energy consumption that is higher. We have more consumptions of energy, more heat released from the cell, and so more accidental work and less useful work. And so what does it mean? That if the useful work is decreasing or changing anyway, obviously also the electric potential, it will be different. And the kinetics aim is this one. Imagine to speed up the process, so actually promoting the process with a real current in this case, so avoiding the presence of infinite resistance. What is happening is that since the useful work is changing, is decreasing, also the electric potential is modified, the reduction potential is modified, and the final of the electrochemical kinetic is to describe the relationship between the potential as a function of the current. If we reduce the resistance in order to ensure a real current, we can say that the potential, the reduction potential, it will change. And in particular, it will change in a way that is different with respect to the equilibrium potential. So if we want to say that the equilibrium potential is the open circuit potential, so the same types of potential that we can appreciate in the Nernst equations, for instance. Imagine that the resistance is going to infinite and the current is basically zero. When we are increasing the current is basically a measure on how much our reaction is proceeding, so how much our reaction is faster. Higher the current, higher the speed of the reaction. And if the resistance is a real value and is not infinite, we have even a value of the current, a real value of the current. And if we have a real value of the current, the potential is moving away from the equilibrium potential and is a new real potential. The difference between the real potential and the equilibrium potential take the names of overtension. And why this concept is so important? Why is it so important to know about the overtension? Because overtensions basically tell us in which way our reduction potentials of one electrode associated with a specific reaction is varying in the moment in which a current can flow. And it varies more if we are increasing more the current, because we are decreasing a lot if you are running a lot of current. So if you're running a lot of electrons, we have a huge current, we have a huge decrease in the useful work, and important changing in the real potential with respect to equilibrium 1. And so if we want to use, for instance, a battery, and so we have a chemical reaction that can promote the generations of a DDP. And the DDP, we know, is the difference between the reduction potential of one electrode with respect to the other one. And the DDP, obviously, from a theoretical point of view, only considering thermodynamic concepts, is the difference between the two equilibrium potential, the two open circuit potential associated with the two electrodes. But obviously, this DDP, the theoretical one, that is also the maximum, is not a real DDP, because in the reality, the final output, the final voltage of a battery is smaller. So if we have a battery, here for instance, if we have a battery composed of two electrodes, and we have an infinite resistance, this resistance is infinite, since we know that the entropic contribute is the smallest, we have that basically the voltage generated is maximum. It's basically the difference between this DDP, the voltage generated is the difference between the equilibrium potentials of this electrode with respect to the other one. But in the moment in which the resistance is not anymore infinite and we are running faster the reactions and we can appreciate a real current, well, this DDP is decreasing, because this is changing and this is changing, and these potentials are changing in a way in which the useful work decreases, and so the final total DDP is smaller. So a real battery works with an output voltage that is always smaller with respect to the theoretical one, because the theoretical one is based on an assumption, and this assumption is the open circuit condition. But we know that working in open circuit condition is only an imaginary situation, because in the reality always we have a current. And this is for what concerns the galvanic cell. And for what concerns the electrolytic, in which we need to apply a certain potential in order to promote a non-spontaneous reaction, well, in electrolytic cell, from the other hand, if the theoretical voltage we need to apply in order to promote a certain reaction has a specific value, in the reality, since we are not in open circuit condition, we need to apply more potential. So if maybe the electrolysis of water required theoretically 1.23 volts in order to generate hydrogens and oxygens from water, as in the case described in the Purbe theorem. But in the reality, we need to apply more energy, because some of this energy is just simply lost, and so we need to apply an additional voltage. And this additional voltage we need to apply it in order to promote a non-spontaneous reaction in an electrolytic cell, or the smaller amount of voltage generated in the DDP in a galvanic cell with spontaneous reactions. Well, this difference between the real actual voltage and the equilibrium one represent the overtension. And the Kinetics describe the amount and the intensity of the overtension, the difference between the real potential and the equilibrium one, as a function of the current. So now what we can say is, imagine how actually a redox reaction is proceeding in the reality. So we need to consider, for instance, an hypothetical reduction. So we have one species, and we are imagining that this species is one to be reduced in another one. So we want to proceed in this direction. What is happening is that our reagent should migrate at the very beginning from the bulk in an interface approaching the surface of the electrode. And so we have a first movement, a first transport, a first diffusion between the bulk and the surface. So a mass transport, basically. Then we can even have a chemical reaction. This is not always present, but it's important to remember that sometimes the species that undergo reductions is not the same as the bulk, but it's not always present. Then we have the absorption, and then we have the electron transfer. So on the surface of the electron, we have actually the changing in the electrons in order to pass from this species to this one. And obviously, again, the desorption, eventually chemical reactions, and the mass transfer, the diffusion. Obviously, these type of situations can proceed in both the two directions. It depends on the polarizations of the electron. We have described, for instance, speaking about the Fermi energy, how improving a negative polarization we are promoting the reductions, whereas polarizing positively we are promoting the oxidation. So we are pushing the systems in one direction or in the other one just by selecting the directions of the electron in this way, or in the other one maybe with a potentiometer. So okay, what is important to say is that, okay, we have, if we are actually running with a real current our process, we have some loss in energy, we have some reductions in the useful work, the reasons for which our electrode potentials is modified, and so the final dP and so on. And this is due to the fact that when actually we are running our process, we can meet different types of resistance in each single step. So maybe a resistance due to the mass transfer, so an overpotential contribute due to the mass transfer, resistance due to the mass transfer, and overpotential due to the mass transfer. We can have a resistance due to the diffusion of our reagent in the bulk, on the surface, and in each single process involved here. For instance, a resistance and a connected overpotential due to a reaction. So resistance and connected overpotential due to a reaction. And we can even have a resistance and so the corresponding overpotential, the corresponding changing in the actual real potential with respect to the equilibrium due to the core of the process, the real electron transfer. Resistance to electron transfer, resistance due to the reaction, resistance due to the mass transfer, and the correlated changing in the potentials, and so the correlated overtension. So now what is important to say, focusing about the final aim of electrochemical kinetics, is that we want to solve this function. And so in particular look at this function. So the real potential minus the equilibrium one as functions of the current. And so basically what we need to know is the contribute of the overtension. So how much we are moving away from the ideality, this is the overtension, as a function of the current, or the current density. That is basically the current over an area. So this is current over an area. Sometimes we can even look at current density. So what is important now is that we can have different process involved during the passage from this species to this one, have described here. And each of these single steps lead to a certain resistance, a certain efforts, a certain obstacle that our species or the electrons should do in order to ensure the realizations of the reaction. And so if we want to say that plot in a diagram potential versus current density, because we are interested in this function, so it would be even an overtension, but now it's better to use a potential. No, yes, let's try with the overtension maybe. Overtension and current density. When we are at zero, so when the current is zero, this means that the resistance is infinite. And so what does it mean? That the equilibrium potential is equal to the real potential, because we are in an open circuit condition. And so, here, basically, we have 0 as overtension. If the current is 0, the overtension is 0, since the actual real potential is equal to the equilibrium 1. But in the moment in which we are increasing the current, the overtensions increase, because we are moving away from this situation, and this is start to become different from this one. And so we can have different steps of profile due to the different steps of obstacles creating this overtension. For instance, we can have a profile like this if we are imagining to consider only the obstacles due to the electron transfer process, the real core of the process, so the exchange of the electrons on the surface of the electron in order to pass from one species to the other one. But we can even have something like this if we are imagining as the main contribute, so the limiting contribute, only the ohmic resistance due to the passage of electrons inside the wire, for instance, and so on. This is a straight line, since the ohmic resistance obviously follows the Ohm's law, and so basically we know that the relationship between the current and the voltage in the Ohm law is basically a linear relationship. And then we can even have a contribute due to the generations of overtension involving the diffusion and in particular the mass transfer. And so actually something that is quite close to the concentration and how much the concentrations of one species can fight the generations, or can fight the reachings of the maximum useful work, and in which way basically the concentrations of our species involved in the chemical reactions can modify the final output voltage. But this is something that we need to investigate as a last step of this kinetic description. And in general, it's important to appreciate also here how the generations of overtension start to become more important in the mass transfer contribute only when we are approaching very high current, when we are close to the limiting current. We will see what is a limiting current later. So basically, in this case, we are imagining to appreciate the resolutions of this function. Imagine to consider one types of obstacle, another types of obstacles, and another types. Ohmic resistance, mass transfer, and electron transfer. The final totals contribute, imagine to sum each single obstacles, leads to the fact that we can obtain something like this. We are obtaining something like this. And in the reality, this is exactly what we can obtain in the moment in which we are polarizing two electrodes with a potentiometer. If we are polarizing two electrodes with a potentiometer, maybe we are proceeding with a linear voltammetry analysis. So we are applying a potentials and we are detecting the current. We can exactly appreciate in the reality something like this. So we can appreciate something like this because we know that for each single overtension we have a specific current, and increasing the current we have a specific overtension, we have a specific moving away from the reality, but this moving away has always this specific shape. Obviously it could be a little bit different regarding the nature of the species involved and the natures of the electrode and so on. We will see different characteristics and how, for instance, the Butler-Volmer, we will see what does it mean Butler-Volmer equation is fundamental for the comparisons of electrons considering this aspect. But in general, we have always this shape, and this shape is due to the contribute of electron transfer, is due to the contribute of ohmic resistance, and is due to the contribute of mass transfer. So basically, this is the point. And in the next lesson, we will start speaking about the resolution of this function, considering as single obstacles, so a single contribute due to the generations of overtension, the electron transfer. Why? Because we want to solve these functions separately for each single steps of obstacles. Imagine that that obstacles is the limiting one in order to simplify the mathematical description. And we need to solve this equation starting with the surrounding conditions, imagining as the only one obstacle the electron transfer. Then we will do the same, but this is extremely simple, with the ohmic resistance, because it's just a line, so we do not have real demonstrations for that. And later, we need also to solve these equations considering the mass transfer. That is the limiting step always when we are approaching high current. And so, when we have solved these three functions with these simplification conditions, we can bring them together and say, okay, this is the reason for which we have this specific shape. And this is basically what is important for now. Let's see the next lesson, in which we are going to speak about the Butler formula and the resolutions of the overtension as functions of the current in the case of electron transfer limitation.